In the last session, we had dealt with how to find bootstrap confidence intervals. So, we had learnt about the various bootstrap confidence sets and bootstrap confidence intervals. In this session, we shall be seeing the computational techniques or the computational methods for bootstrap. So, there are certain issues that needs to be kept in mind. The first is that bootstrap is a very computational intensive procedure. So, efficient methods are needed for saving the time and saving the computing expenses. Also, there can be issues like how many bootstrap samples needs to be taken, so that we get a efficient answer or an efficient result. In this session, we shall be dealing with some of these aspects. The jackknife and the bootstrap are computer intensive methods, and special attention needs to be paid to computational details, because one, we need efficient methods because they are necessary for saving time and computing expense, and questions such as how many bootstrap samples should be taken needs to be considered. Now, assume that x1, x2, xn are IID coming from a distribution f, and in this session we shall study some results on efficient numerical computation or approximation for the jackknife and the bootstrap. Now, let us consider the jackknife first. The jackknife estimator VJack. In some special cases, explicit formula are available. Example, if Tn is equal to xn bar, we know what is the functional form of VJack, and we can use that to good effect. Now, there can be cases where explicit formula are available for complicated statistics. For example, if we take the L statistics, it can be shown that the L statistics has a form Tn is equal to I runs from 1 to n C n I x order statistics I. It can be shown that variance of jackknife has the formula y transpose W y, where y is the order statistics, a set of order statistics x1 to xn transpose, and W is n cross n matrix with elements Wij, where Wij is of the form given below. Now, using this form, we can compute the VJack. So, in general, the variance of the jackknife estimator involves the calculation of the given statistic Tn n times. Now, this may be cumbersome if Tn does not have an explicit form, or if n is large, because then if n is large, then the same thing needs to be computed n times. Now, one can use the one step jackknife procedure to at least bypass some of the computational burden. So, the one step jackknife procedure, we assume here that the statistic Tn is the solution to an iterative procedure, that is Tn is limit k tends to infinity Tn k, where Tn k plus 1 is g Tn k Fn k equal to 0 1 2, where Fn is the empirical CDF and g Tg is a known function. Now, if we define f tilde n I epsilon is Fn minus epsilon delta xi by 1 minus epsilon, and Tn I epsilon 1 g Tn f n I epsilon tilde, this 1 signifies the first iteration of this with initial points Tn I equal to 1 to n, and let g prime Tg is delta g delta t of derivative of g Tg with respect to t. Then VJack for Tn is estimated by this given form, which is a bit complicated, it is written here, and see it does not require any iteration in the computation. So, in practice epsilon is usually taken to be 1 by n, and there if n I epsilon approximately is equal to f n minus 1 I, the empirical distribution based on n minus 1 observations x1, x2, xn, xi minus 1, comma xi plus 1 to xn, that is x1 to xn excluding xi. Now, in case when n is very large, we may need to find an approximation of VJack requiring fewer computations, and one such technique is the grouped jackknife. So, what we do here is we divide the data points into m groups of size g such that the total number of observations n is equal to mg, and then compute T n minus g I, that is we compute the statistic leaving apart the ith group, and the given statistics based on the data with the ith group of, so that is the given statistics. So, T n minus g I is the statistics based on the data with the ith group of observations removed. So, the group jackknife variance estimator is V G, G stands for grouped, G jack, m minus 1 by n summation I runs from 1 to n T n minus g I minus 1 by m summation I runs from 1 to f T n minus g comma j square. So, that means as if we are taking the entire data, dividing it into groups, and now each group acts as if like a single observation, and we perform a jackknife on those grouped observations. Note that the advantage here is the computation of VJack requires m evaluation of the given statistic and not n, but m. So, that means, so n by m is g. So, we have reduced our effort from n computations to m computations, which is g times. The question is how to divide the data, and if there is no clear way to divide the data sets, the groups have to be formed randomly. So, if this is done, expectation under G V G jack is 1 minus 1 by m V jack minus g minus m minus 1 square by m n n square summation over all these quantities T n minus g s, where T n minus g s tilde minus T n bar, where s tilde belongs to s and s intersection s tilde is phi. So, there are no common elements, and E g is the g here, meaning that the expectation is taken with respect to the random grouping. V jack minus g is the deleted d jackknife variance with d is equal to g. So, there is a technique called the deleted d jackknife, and so that we get that variance jack minus g. N is n c g, n tilde is n minus g c g, s is all collection of subsets of 1 to n with size g, and T n bar is 1 by n summation s belongs to s T n minus g s. In the same m evaluations, we may also use random subsampling, that is, we can draw a simple random sample, say I1 to Im, without replacement from 1 to m, and approximate V jack by Vs jack, which is n minus 1 by m summation I runs from 1 to m T n minus 1 I minus 1 by m summation I equal to 1 to m T n minus 1 comma I square. Now, if Es is expectation with respect to the selection I1 to Im, then Es of Vs jack is 1 minus 1 by m 1 by m minus 1 n minus m into V jack. So, that is a correction factor into V jack. Now, we move for computational issues arising for the bootstrap. So, like the jackknife estimator, the bootstrap estimator have explicit formula only in a few cases. In most of the cases, Monte Carlo approximations are used to compute the bootstrap estimator. Now, let P r hat is an estimated model using data x1 to xn, and V boot is expectation star r n x1 star to xn star f n hat minus r n x1 to xn p n star. So, that is the bias for the boot. So, the variance for the boot is variance star r n x1 star to xn star comma p n hat, and H boot x is probability r n x1 star to xn star comma p n hat less than equal to x, where x1 star to xn star is a sample from p n hat, E star, V star, variance star and p star are computed with respect to p n hat given x1 to xn. Now, to apply the Monte Carlo method, we begin with generation of B independent samples x1 star B to xn star B B runs from 1 to capital B from the estimated model Pn hat. Next, we can calculate Rn star B, which is Rn x1 star B to xn star B Pn hat. B runs from 1 to capital B. Now, based on this, we can then compute the bias of the boot based on the B samples is 1 by B summation B runs from 1 to capital B Rn star B minus Rn x1 to xn Pn hat. Similarly, variance of boot can also be obtained as 1 by B summation B runs from 1 to capital B Rn star B minus 1 by B summation B runs from 1 to capital B Rn star B whole square. So, that is the values Rn star B minus mean of those Rn star B whole square, and the H boot x is 1 by B summation I runs from 1 to B I Rn star B less than equal to x, which is the indicator or the empirical CDF. Empiricals. So, H boot Bx is 1 by B summation I equal to 1 to B I Rn star B less than equal to x. So, that is the empirical CDF based on the bootstrapped observations. Now, x1 to xn follows f, then Pn hat is equivalent to f hat, which is the empirical CDF, and x1 star B to xn star B is simple random sampling with replacement from x1 to xn. Note that a typical sample is of the form xi1, xi2, xin, where 1 is less than equal to ik is less than equal to n. So, this problem is equivalent to choosing a simple random sample with replacement I1, I2, in from 1 to up to n. What should be the number of samples chosen? So, what should be capital B? Well, capital B can be much larger than n, but we should choose B so that the error of the Monte Carlo approximation is negligible with respect to the error of the original bootstrap estimator. Now, Efron considered the CV as a measure of variability of the Monte Carlo approximation using a fixed B. Now, the MC approximation, the Monte Carlo approximation to the bootstrap standard error for an estimated theta hat n is S boot B, which is based. So, this capital B stands for the fact that S boot is based on this capital B observations is equal to square root of variance of boot. Now, the standard formula for moment estimator gives that E star S boot B is approximately equal to square root of V boot, and variance star S boot B is approximately equal to the quantity, that is rho boot minus V boot square by 4 BV boot, 4 B into V boot, where rho boot is equal to expectation of theta n star hat minus expectation of theta n whole to the power 4, and then we can compute the CV of S boot star, which comes out to be approximately delta n hat plus 2 by 4 B square root, where delta n hat is rho boot by V square boot minus 3, which is conditional nothing but the conditional kurtosis of theta n hat star. And using the CV and fixing that CV to a given quantity, one can choose the desired number of bootstrap samples. In this session, we have learned about some of the computational issues associated with bootstrap and jackknife. In situations where explicit formula for bootstrap and jackknife is available, computational burden is reduced. However, in most situations where the explicit formula is not available, one needs to take care of the efficiency of the algorithm, as well as one needs to answer how many bootstrap samples needs to be considered. So, in this process, we have learnt about the one-step jackknife procedure and the group jackknife procedure. Also, we have learnt the CV measure or the coefficient of variation measure in context to bootstrap, which determines how many bootstrap samples can be chosen.